part of the code which relates to flat slabs. I've been able to get a copy put onto your files. Okay, and we've paid copyright for it, so we're licensed to do it. It's a license for e-copy, so just remember that. Okay, that's what I've got permission for. And also the table 15, which was not in Greg's book. And I've managed to get a copyright for that as well. So those two items have been put on, okay, onto the files. So please download them, make sure you have them. All right, it's important. All right, let's move on to flat slab. Now in Greg's book, it is discussed from page 4.7 on leading on to all the way through to basically page 411. Sorry, that one's turned around the wrong way. And then I've put some stuff here, 411, 412. And then, of course, some of the things which the additional topics following on from that, I just left them in there as well, just for reference purposes. And of course, the punching shear as well. Right, we're going to look at this now in terms of an example. So let's go to the example then. I'm going to use the example from Greg's book. Okay, so we'll start with that first, flat slab. Okay, so here we have flat slab constructions to be used for the floor of an office block with planned dimensions of 40 by 30. The columns will be spaced at 8 meter centers over the length of 40 and at 6 meter centers over the length of 30. So what you're saying is you've got in one direction 40 meters and in the other direction 30 meters, right? So you've got 30 by 40. In this direction you have 5 by 8 meters. And in the other direction, obviously, you'll have 6 by 5, 5 by 6 meters, right? So that's it. You've got an 8 by 6 tunnel story, right? The perimeter of the slab is supported on 220 load-bearing brickwork. So at the edge, you've got brickwork, and stability to the structure will be provided by shear walls. Okay, so that's necessary for us to be able to use the simplified method in the code. If we didn't have that statement, for example, stability provided by shear walls, we'd not be able to use the simplified method. 25 cover is required to all reinforcement. The finishes of the slab will approximately be 1 kilonewtons per square meter. The live load is 4 again. These things, this one in particular, 4 is less than 5, is applicable to the simplified method. The columns are 350 by 350 square with the 1.6 meter square head, right? So there's no drop. Understand that there's no drop. This particular column has a column head, but no drop. The slab doesn't have a drop. So drop is one where you would have, for example, let me just pick up a picture that I was dealing with earlier, so you can see what I'm talking about. Okay, so here's a drop, right? So now here, there's a drop here. So in other words, at this particular one, there's the drop. Right, and this is the column head, just so there's no misunderstandings and everybody knows exactly what we're talking about, right? Because there's specific rules with regards to the division of the strips when you have a drop and you don't have a drop, etc. So those things are important to understand. All right. Okay, so coming back to this, all this particular example has a drop. It has a column head, no drop. Use grade 25-26 concrete. The column heads are 1.6 meters square. So don't forget, when it comes to the term HC, all right, which is used in the code, then there we have to find the equivalent diameter, basically, assuming that we convert this area to a circular area. What's the equivalent diameter, right? For the interior edge panel on the 40-meter length, shown shaded below, check one of the interior columns for punching shear and check the panel for deflection, all right? So we start with LM. What's the mean for the average length? It's 8 plus 6 divided by 2 is 7. No drops. Okay, so H is equal to LM divided by, now this is given in Greg's book somewhere, that it's 29 or 31, depending on whatever. So a suggestion is we use this value divided by 29. So need probably, let's try 250 millimeters. It says you need about 241. Let's try 250. Self weight is 6. The finishes are 1. So it gives us 7 for dead load. Live load is 4, which is given. All right. So we've got the dead load. We've got the live load, nominal loads, unfactored loads. OK, we have to factor them up, 1.2 and 1.6. Remember, at this point that you must have only this load case, very important. All right, for the simplified method is dependent on one load case only. There are no multiple load cases in the simplified method. All right, so you must use the fully factored design load. All right, then we look at the angle of the column head. So basically what you're saying is you've got if you look at it like that, there's your column in between, which is 350. And then on either side, you've got those dimensions, which will be 1,600 minus 350. What does that give you? 1600 minus 350. You're dividing that by 2, so you got 620. This is a live lesson. You make notes. Okay. I'm not interested in video issues. It's got nothing to do with me. As far as I'm concerned, my class is live. The recording is just a convenience. Okay. I'm not guaranteeing that the thing will be recorded or you'll be able to watch it 150 times. If you are sitting in a normal classroom, you'd be sitting with your notes and a pen and a paper. You might record it personally for yourself, but as far as the general rule is that you make notes. Okay, so I expect that's what you're going to do. This is not a passive lecture. This is a lecture that's meant to be active, interactive with students. Okay, area of column head 1.6 by, so this is checking that you got 625. As you can see, that's 45 degrees. So that's okay. Area of the column head is 2,56. The next step is to convert this area to a circular area. So if you remember, d squared would be equal to 4a, or let me write it from the beginning. So you'd say pi d squared divided by 4 is your area for a circle. All right, so that's going to be equal to area. So basically what you're doing is you're saying d squared is equal to 4a divided by h. Please annotate these things in your textbook so that when you come to the tests or assessments or whatever, right, you know what you're doing. D is equal to, therefore, the root of 4a over h. So that's how you get to what's there, right? So 4 times 2.56 divided by 1.805, sorry, divided by pi will give you 1 meters. All right. The next thing is, what is a quarter LM? Now this comes in as a check from clause 4.6.1.3. This is A, this is part A of that clause, and this is part B of that clause, okay? In your book, it's covered on page 60, I think. Sorry. Yes?
Okay, no, never mind. Yeah,
Sorry?
I couldn't see your screen. It came back now.
Okay, sorry. All right, so 4.6.1.3a, part A of that. In the textbook, it's page 4.7. Okay, I think this is 4.7. Yeah, page 4.7. And this part here is also at the bottom of page 4.7. So where does this thing come from? You know, you either look at the code. When I put the square bracket in here, it means a textbook, right? So that's from the textbook, okay? So 8C is 1.25 times 7, and 1/4 is 1.75. So the head is actually greater than that, therefore 8C is 1.75. You can't exceed 0.25, all right? In calculating the value of 8C. So whatever it comes to, you have to restrict it to 0.25 LM. Okay. You look at page 4.7 at the bottom there, it says the second paragraph up from the bottom may not be taken as greater than 0.25 times the average dimension of the panel. Okay, check requirements for simplified analysis. Stability is provided, that's okay. Dn over ln over dn, so in other words, the live load is less than 1.25 times ln over the ratio of live to dead does not exceed 1.25, so that's there. Live load does not exceed 5 kilonewtons per square meter. We got that. More than 3 rows in each direction. We're okay with that because we worked out in the beginning 5 panels, and here we go. There it is, 5 panels in that direction, and what's it? 1, 2, 5, 5 here, and 1, 2, 3, 4, 5, 5 by 5. So we've got more than 3. That's rows in each direction. All spans are equal in each direction. It doesn't have to be equal, it has to be approximately equal, okay? So just make a note of that one. All spans are approximately. Not equal, it has to be approximately. And the same thing that we used earlier on, where we said it mustn't exceed the one span by 15%. You can use the same sort of guide. So there's nothing written down, but you can use that guide. Ly over Lx is 8 over 6, 1.33, which is less than 2. Okay, now we're looking in the 8-meter span. Usually now in restrained slabs, the short span is a critical one. But when it comes to flat slabs, please be careful. The long span is a critical one, right? So in flat slabs, when it comes to flat slabs, please note that the long span is critical. Long span gets the bigger depth. So normally when we're dealing with restrained slabs, okay, when we're dealing with restrained slabs, we put the main reinforcement in the short span, right? But here we're going to put the main reinforcement in the long span, gets the larger D. Okay, so just keep that in mind. Okay, right, so we've got the strips, the middle, the half, etc. Width of the column strip is 0.5 times Lx is 3. Okay, if you subtract the total from that, so you've got 6 minus 3, which is 3. Dy, 250 minus 25 minus 6. You see here, this becomes the first layer at the bottom. So what we're saying is, all right, dy is this steel here. That's dy, and dx is going to sit on top of that. So dx will be that one. Do you follow? So dy is the lower one, so we get the larger value for d, assuming y12 bars in the first layer. Flat slabs, depending on the span, can go up to quite large areas of steel, diameters of bars as well. You could see 20s and 16s, not unusual, depending on the spans, right? Very, very popular for parking garages, as I told you, and open spaces which don't need any interruptions in the floor space. It's more suited to that kind of thing. L1 is 8 and L2 is, so we're looking in the long direction. So in the long direction, this is the direction that you are spanning. Please keep this in mind, right? So the direction of your span is L1, understood? You are spanning the long direction, so therefore that becomes your L1. When you span the short direction, then L1 will be 6. It will go vice versa. All right, so your L, your effective length for like how you have effective length of a beam, effective length of a restrained slab, etc. The L becomes L1 minus 2HC over 3, right? So L1 is equal to 8 minus, remember it was 1 point, the heads or 1 point. What did it work out to? 1.805, which was greater than a quarter of the LM, and therefore we had to reduce it to 1.75, right? So don't forget, this is that 8C, so be very careful, make sure you calculate in the right value there. 8 minus 2 times 1.75 divided by 3, which is 6.83. Okay, and then we move on to what is F? So F is equal to N times L times the other length. That's the way I like to remember it. N times the load times the effective length times the length in the opposite direction. In the perpendicular direction. So 14.8 is the UDL, 6.83 is the effective length, and 6 is the direction, is the length in a perpendicular direction, giving me a total of 606.1.5. So one panel, whichever way you want to look at it here. So we're talking about this one panel. This is the load on one panel. Give me a second. So this is the load on the panel, on a typical panel. Right, so we look here, this is the load on a typical panel. Take a typical panel there, right? And that's the load on it. Right, the total load on that panel is going to be 600 and, where did we find it? 606.5. All right, if you have a question, just unmute your mic and take it from there, all right? Please, because this thing is, I'm not saying it's complicated, but it has a lot of detail. So if there's something you're not happy with, please just interrupt. I don't mind. All right, so we're done with the calculation of the effective depth. We're done with the calculation of the force. Now we go to the table, right? So we go to the table, if you prefer, in Greg's book or in the code, since most of you have the book in front of you. We'll go directly to that, right? And it's going to be on page, on page 4.9, right? So we're referring to page 4.9 in the book. Okay, so that's page 4.9 is where it starts and goes over onto page 4.10. All right, please look at the code. Please look at the code, because in the code table there are some notes. It's on page 67 and you've been given a copy. All right, it's on page 67 of the copy that I gave you in the code. It comes up on page 67. All right, so please look at that. That is table 16. Right, this is table 16 of your code. All right, as I said, on page 67. And what we have there is we look at the table. Maybe I should bring that in now, and then we can see how it applies. Page 67, so let's go back to it, sorry. Oops, there we go. Right, so there's page 4.9. Table 16 is used to determine the total bending moments and shear force. All right, it's not per meter, it is total, so please be careful. All right, so we've got the outer support, we've got a wall, right? In our case, the outer support is a wall, not a column. 220, yeah, load-bearing walls. So we have this situation here.
Excuse me, sir.
Sorry?
Just a quick question. So in flat slabs, we always calculate our slab thickness. It's not something that we're given.
No, it depends. Like in a question, like in an exam or assessment, obviously we're looking at both design and assessments. Remember, I keep telling you that. So in an exam situation, probably be given to you. Okay, because I wouldn't want 55 different answers. Yeah, if it comes to an online test, then we could do something like that. Okay, so wall 0.02 FL and the shear will be 0.4. Okay, then we're going to look at the first interior support near middle of end span at first interior support at middle of interior spans at interior support. So what have we got? We've got a panel in the short direction. In the short direction, it's first interior support, right? And near middle of end span, so that'll apply to the short direction, right? In other words, the 6 meters, okay? And when we come to the long span, then we're going to go to at interior supports. So let me change this. Now we're going to look at interior supports and middle of interior supports. Once we've done this, we've then got to go to this table and sort it out in terms of column strips and middle strips. Okay, right? So there's the effective span, which is the L, and that's where you find the L1 minus 280/3. This is in the table, but Greg's put it on the, what do we call it? On the sketch here, right? But just remember, so L1 is in one direction, L2 is in the perpendicular direction. So if you're looking at it in the Y direction, then obviously these two swap around. Okay, the bending moment coefficients obtained from table 16 can be presented on a bending moment diagram as shown. Okay, 0.02, so you see that this is the one we're using. If you remember, because we've got a wall, so because we've got a 220 wall, just be careful. Therefore, we didn't use 0.04, we used 0.02. Right. Then above 75% to column strip, 25% to middle strip, and then your sagging moments have 55% to column strip and 45% to middle strip. Okay, right. This part here, sorry, which is upside down, let me just get over with what this is about. This is about when you have a column, right? And the moment you need to check whether the moment on the column strip, okay, coming to the column where there's no beams, there's no other supports at that end except the column directly, then there's a limitation of how much that column can carry. So that comes in with that. And again, I want to refer you to that book by Marshall and Roberts. There's an example where they use this part of the code to describe what's going on. All right. So there's an example. There's no example in the book that we've got, but there is definitely an example in Marshall and Roberts. There's actually a number of examples which are very, very useful because there's examples of a panel with just a column. Then there's one with a drop, and then there's one, sorry, with a drop and a flared head, and then there's just one with a flared head without a drop. So we've only got one. There's like multiple examples there, except as I told you, just be careful. Some of the information regarding the codes is not applicable. We have new values to consider. So middle positive, right, is going to be 45% of 0.071 FL. We spoke about that. We took it, remember, from the we're dealing with the long span. So all of this is coming from the long span, right? This is coming from the long span, interior supports. Going back to the table, I'm just going to make sure that you know what you're picking up, right? That's why I'm doing this, sorry. Give me a second to cross-reference. So what I'm saying to you is, oops, turn it around. Okay, so let's see if I can. Yeah, so this table here, you see that middle of interior spans, I said the blue ones are applicable to the long span and the yellow ones are applicable to the short span. So just remember that, right? Okay. So going back, right? That's why I highlighted that in blue, because it's coming from the, all of this is coming from the table, the 2 rows at the bottom, interior spans. Okay, so just to remind you, it's because it's from the, it's an interior span. Sorry.
So,
yes.
As you choosing from the table that you're choosing from, when you're talking about the middle position and middle negative and stuff, here you're talking about you see the picture or the drawing in page 4.30. As you're talking about the long span and the short span, you're talking about that sketch, or you're talking about the whole floor on page 4.28.
In the example here, we're talking about this now, right? See, we are going in this direction. Give me a second here. Right, so we're going in this direction. We're looking at that span. So just focus on the span that we're talking about, all right?
Okay, so if you're saying like, can you go to the table that we just looked at? You said we're looking at the wall, right?
Okay, first just let me clarify something, because I'm guessing, I think I know what's troubling you. So tell me if I'm right. Okay. You see, this panel is an exterior panel, correct? But in terms of this direction, in terms of that direction, we can consider that as exterior, right? And in terms of this direction, it is considered interior. Okay. Are you with me? If you look at the 8, this is the 8-meter span here, right?
Yes.
Okay, and that side's the 5. So listen carefully to what I'm saying. So when you look along the 8-meter length, you've got continuity on both sides.
Yes.
Right, is everybody happy? And when you look at the 5-meter span, you've got continuity on one side.
Yeah.
Right, at the top, it stops where the brickwork is, there's no continuity. Makes sense now?
Yeah, it makes sense.
All right, so that is why when it comes to the 8-meter span, we're using the internal, the one that I hatched as blue. Where is it? Yeah, these two here. Can you see that? I shaded them in blue because those are the exterior ones, all right? And then for the interior ones, I use those.
Okay.
All right, so just if I said, if for example, we said we wanted to design the an interior panel completely. So let's say we wanted to design a panel here. Are you with me? Now we'd only be using the blue ones.
Okay.
I know this thing it tends to become a bit confusing, right? Because like there's a lot to sort of go back and remember. So just please, if you have a questions like what you had just now, thank you. I'm sure it helps clear some things up for the rest of the students as well.
Okay. So
Okay, because I'm telling you that I did this thing and then I'm looking at it again after a while and I had to go and really read carefully and make notes between the code, Greg's book, Marshall's book, Mosley and Bungie. You know, it takes, it is a bit challenging to sort of remember all the stuff that needs to be remembered. And it doesn't seem to be too easy to write down a, what do you call it, a flow chart, because you've got options. So you'll have to write flow charts for various options. You'll have to write a flow chart for a flat slab with only a column, no heads, no drops. And then you'll have to write one for a column with column head, and then whether the column head exceeds the quarter or doesn't exceed the quarter. And that's already a split of 2. And then you've got one with a drop. I mean, you look at the one with the drop, does it exceed 1/3 or it's less than 1/3? So my God, there's a lot of stuff that you've got to try and remember. Okay. All right. Anyway, let's go then. So now the next part is the 45%, 25%, 55%, 75%. So now we go to, again, Greg's book for convenience because we don't have the code. And there we go. Negative moments will be 75, 25. Okay. And positive moments, 55, 45. So there it is here. Okay. So negative moments, 75 to 25 in the middle strip and then 55 to 45. All right. Okay. So please keep this in mind. Otherwise it becomes very confusing. So going back to the example. So that's why he's put middle first and then column 7. You know what I'm saying? So, all right, but remember, just going back to it, it's negative and positive. So focus your attention on that. So the negative and the negative. Can you see that? Is a 25, 75. So that's one part of the table, all right? And then another part of the table is the positive ones, which you've got to be careful we don't mix this up. So that's the positive there and the positive there. Are you with me? So please do these kind of annotations on your textbook so you remember how it's used from the table. Okay? Otherwise, it's very easy to make a mistake here and put the wrong percentages in. So 45% from the middle positive and column positive 55%. Why do we have this? Why do we have this variation in the spread of the load? Why can't we just say 50% goes into the column strip and the remaining 50% goes into the middle strip? I explained this to you at the previous lecture. Why? Can anybody remember? The reason, if you remember that thing that I showed you, is that when you're on the column center line, your moment is peaking. Now this is from experiments, right? And as you move away from the column center line, going in, all right, in a direction perpendicular to the length that you're considering, then in that case, you'll find that the moment deviates, it goes down a little bit. Okay, so just keep that in mind. I must get permission to share something with you from Marshall's book where he discusses those experiments. Okay. If the library were open, I mean, if we were allowed on campus, then the library had a book and you put it on short loan reserves where you can't take it out, where you can just look at it and refer to it. I must look at some way of getting you access to that. Some very important notes and examples in that book are very, very useful. Okay, let's see if I can arrange some copyright for that. All right. I think let's sort of try and keep a balance, right? The focus for us will be on the textbook and on the tutorials, okay? Broadly speaking, in practice, we need a lot more than that. And I will try and make that available by getting the copyright for the relevant parts. It's a lot, but I'll try my luck. Let's see what happens. Okay, don't make any promises. I'm going to try. Okay, middle positive, because yeah, there's a lot of information in different places. So let's see what I can arrange. Okay, it's nice to see the whole picture. Ideally, you've got all the stuff. You put it away, and when you get back to work and you end up in a structural office and you have to design a flat slab, quickly you've got access to the information that you need, right? Because the code by itself is just a legal document that covers the major issues. The in-depth commentary on that is in a book like Marshall. Okay, you'll find it there, or Mosley and Bungie, or A.H. Allen, one of those textbooks, right? Okay, so as I say in Greg's book, we've got one example to work with only, unfortunately. So I'm giving you these other references, okay? And as I will try to get a copyright for the relevant pages, especially for flat slabs. The other ones I think we can get away with, but I think for flat slabs you need that reference. It's important. There's just one more minor issue which I'll come to later on. Just remind me about the shear stress, and of course, yeah, I think that's one of the issues that is a bit different in the Marshall book because it was written before the code was changed. Okay, 132.3. So we've got these moments. All right, 132.3 kilonewton meters, 57, 161, and 170. Do you have to arrange it in this form? Could you have arranged it as the hogging moments first and then the positive ones? Doesn't really matter as long as you know where you are and what you're doing. So middle positive. Remember, we're in the long direction. So if I can just maybe use a sketch to sort of show what we're talking about. Right, so you can relate to it. So that's the panel under consideration. And I'll leave the lines where it is continuous, right? So we understand. Okay, so let's take the middle positive 132.3 and the middle negative 157. So we're saying do it like this: middle negative, middle positive. So it's those ones, right? So that's your 57. That's your, what is it? 132.3. Okay, are you with me? And because it's symmetrical, so I'm not going to bother about the other one. Then column negative is going to be, this is your column here, remember? Okay, so let's put it in a different color, maybe, I don't know. Okay, so we'll say this one is 170.9. There, and here it's going to be, so that was there in the column strip, all right? And then you've got in the column positive 161.8. All right, so does that help you understand what you're doing now? So that's the area of steel that is required in those things that I've drawn. Trying to illustrate the direction as well as where it's applicable. All right, what is the width? The width is 3 meters, remember? We took the column strip 3 meters, and then the middle strip became the total 6 minus 3, which became 3, okay? All right, and then you've got moment per meter for convenience. Now it's difficult to work with millimeters over 3 meters. So what we do is we want to bring it to millimeters per meter in terms of the area of steel. So we take the 132.3 and we divide it by 3. So we take that one, sorry. getting confused which colors to use now, you know. All right, so just to differentiate from different things. So we take that, we take the 132.3. Yeah, I'm listening.
Can I just stop, please?
Yeah.
When you're talking about, you see the column, when you say middle positive, right?
Mhm.
And you write that 132 there in the middle.
Yep.
So when it's middle negative, it's close to the, you see?
See,
I do not
middle
understand.
negative is over the support, because remember the bending moment, just remember the bending moment diagram looks like this. Remember, that's the direction of our span. That's the support, that's the support. So the bending moment diagram looks like this.
Okay.
Right? So when you're saying middle positive, you're talking about that one. When you're saying middle negative, you're talking about that one there. Are you with me?
Yeah, I'm with you.
All right. So even when we're referring to column negative, we're talking about the same thing. It's just that it's in the column strip. Okay. And then it's in the middle strip. So we've broken it up into strips. Okay. So basically what we're saying is, if I could just use this to illustrate that that's the middle strip. Are you with me?
Okay.
That 3 meters there. Okay. And then the column strip, it's not to any scale, so please, if it looks a bit funny, don't worry about it. That's the, as I said, it's not to scale now, right? That's the column strip. Does that help you?
Yeah, it does help.
Okay. All right. So just annotate your book like that, and preferably with colors. The minute you look at it, you know what was going on. Okay. So that's 132.3 divided by 3 gives me the 44.1. Middle negative of 57. And then, of course, same 3 meter story, so it comes to 19. So this is the moment per meter. In other words, we're saying this is kilonewtons. The unit here is kilonewton meters, but it is per meter. So when we want the area of steel, when we calculate the area of steel, we use 1 meter width, not 3 meter width. Do you understand? You can do it over 3 meters. Then what's going to happen is you're going to get a total area of steel, and then you're going to select, say, for example, 12, and 112 is so much, and then you divide the area by that one and work out how many bars you need. So it seems to be easier to bring it back to moment per meter. Okay, but just be careful how you're using this thing and when you're using it, all right? Middle negative, we get 19 kilonewton meters per meter. Column positive, as I showed you earlier, 161. So this is your sagging ones. And then you've got, so if you like, maybe you can put a negative here as a reminder, right? It's written there negative, but you know what, visually, I don't know. 161.8 divided by 3, 53.9, 170.9 divided by 3 gives me 57. So these are all kilonewton meters per meter. Take the K value, and you notice K 0.368, 0.158, 0.45, 0.47. What's the limit for singly reinforced? Quickly. What's the limit for a singly reinforced section? What is K prime? We got two numbers. 0.156 and, come on. Hey, this pen is going all over the place. 0.156 and. Sure. Sorry. 0.156. What's the other one? If I got 20% redistribution, what is it? Can you remember? Because why do I need to consider that one with 20% redistribution?
Because of the
What?
table.
Eh? For the table, correct. I heard somebody saying the table. So what thing in the table is where they've done the 20% redistribution? The hogging moments. Okay.
0.132.
Sorry?
0.132.
That's the one. Thank you. Right. So what I'm saying to you is, in any case, all of these are less than even the redistributed ones, so we're not concerned. All right. You wouldn't, unless you're going to make it a very thin flat slab and you don't put a column head, then you might start to get to very large reinforcement. But here you can see the reinforcement's pretty reasonable, even for a load of 4 kilonewtons per square meter and a 250 slab. Okay, so we end up with Z over D, as you can see, pretty close to 0.95. AS required. Middle negative was 233.95, but you need a minimum of, so that's why this note is here. You need 0.13%, which is 325. So make sure you put more than 325, not more than 233. Is that clear? All right. So it must be higher than 325, not 233. Okay, so we end up putting Y12s at 200, 564, middle positive. Middle negative, you've got Y10s at 225, 353. Column positive, you've got 754, and that's Y12s at 150. Column negative, you've got Y12s at 150, 754. All right, so that's where we're going to put our reinforcement.
So please repeat that comment for me. You said it must be higher than, between two.
So in other words, your middle negative required is 233. When you do the calculation, M upon 0.87 FYZ, right? It comes to 233 millimeters squared per meter, okay? But the minimum steel required is 0.13%. 0.13% is 325. So in other words, what you can literally do is take that one out and write 325. You can't have less than 320. Does that make sense to you?
Yes. Okay, it makes sense.
So now you must make sure, that you got more than 325. Because if you use 233, it'll be less than minimum steel.
Okay, thank you.
All right, you happy with that? Okay, let's continue then. Now we go to the 6 meter span. You can see now we're working with the span in that direction. All right, so width of the column strip, 0.5 Alex is 3 meters. See how it works now. The column strip is 3. So the middle strip now changes, okay, because no longer the, remember in that long direction, we're using a 6 meter width. In the short direction, we're using a 8 meter width. So 8 minus 3, the middle strip is now 5 meters. All right, okay. dy 250 minus 25 minus 12, right? That's the bar that we used in the long span. Now it's the middle of the short span. Okay, 207, assuming Y12 is in the second layer. All right, L1 now becomes 6. Notice the difference. L1 here is 6, whereas in the previous one, L1 was 8. See there, L1 was 8. Okay, so please be careful. Direction you're working in.
We'll add a second layer for the short span with flat slabs.
Sorry, when you just repeat your question. Will you add a?
For restrained slabs, we'll add a second layer with the long span, and with the flat slabs, we'll add it to the short span.
Correct. So you're working like upside down, in reverse. Yes.
Okay.
If you want to think of it that way, that's fine. Okay. So in other words, your main span in flat slabs is actually the long, not the short. The other way around. Okay, that's the difference. I think that's what you mean. All right, width of middle strip 5 meters. Dy is 207. Assuming white 12 bars in the second layer. L1 is 6. L2 becomes 8. So now we get a new effective length, right, which is 4.83. So we go 14.8 times 4.83 times 8, 571.9. You notice this F is different to the F that we had before, 603 something, right? But that's how it's given to us. Middle positive, 45% off, same as we did before. Now we're working in, we've got the middle strip, so it's this part here. sorry, it's this region here. And then we've got the column strips on the side. Do you follow? All right, so we're going to get hogging steel. What color did I use there? Green for middle and brown for column. Okay. Just want to try and be consistent. So basically what we're saying is here for the column strip, right? That's the area of steel that I'm referring to, and in the middle obviously is there. And then in the case of the middle strip, it's going to be there for the positive and here for the negative. And
So,
that one, I'll be with you in 1 second. Sorry. I'm listening. Carry on.
Why on the dy we subtract 12 and 6?
Because, okay. I explained earlier, but I'll do it again. So we're looking at a section of the reinforcement. Okay, I'm looking at it through there, anywhere through there, right? So what I'm saying to you is for this steel, and I'll take the brown one because that's the bar that we're referring to, maybe. Okay, no. Yeah, all right. D here, example is that because it's a hogging moment, right? And then the in the other direction, the same thing had the reinforcement in that direction. So in a similar way, when I come to the sagging positive one, I'm going to put that bar first in the bottom, right? And then I'm going to put the positive in the 8 meter span here. Okay, so this is my dy. Wait. Oh, I mixed it up. Sorry, I have mixed it up. We're looking at the short span. So the short span's inside and the long span's outside. My apologies, I mixed it up. So I'll correct this now. In the short span, it's like that. So this D here is dx, and this one is dy. Okay, so those bars are in the 8 meter span. This one is in the 6 meter span. Does that help you?
Yes.
Now, whether you're looking at it from the top or from the bottom. So if you're dealing with the bottom reinforcement, then remember dx will be from there. Be measured from the top. Are you with me?
Yeah.
Okay, if you're looking at a hogging moment, you're measuring from the bottom. If you're looking at a sagging moment, you're measuring from the top. All right, just be careful which way you're doing it. All right, where the steel is. All right, L1 is 6, L2 is 8. And so we go L is equal to L1 minus 2H. Same thing as we did before. We got the effective length. We got the total load. Middle positive, 45%. And therefore, we look at column positive, 55%. And then we go to middle negative, external, that's 25%. And external column negative is 75%. All right. So interior column negative, 75%, exterior column negative, 75%. And you notice this one has more, right? because you're looking at, you've got that and you've got that exterior there as well. So you got it for the edge one here as well. Okay, and the same thing applies here because you've got a different number for that. So that's why you end up with a table like this. Middle positive, exterior middle, interior middle negative, exterior column negative, interior column negative. Okay. All right. Let's put this down so you can relate to it. Give me a minute. See if you can put a little sketch there. Then we know where the moments are. Okay. So what shall we do? Just use the same green and brown. Okay, first let me put out the panel. So that's the panel. And of course, that's the grid line of the columns now, right? And that side is the wall, don't forget. So now what we're saying is, in that middle strip, sorry, just bear with me as I try and split this whole thing up. So we got the middle strip in here, in this light green thing, because that's the direction we're considering. The span is that way, okay? And I've got here middle positive. Middle positive will be 103.2. Total strip moment. I need to change something here. I need to take a pen. All right, so I've got middle positive is going to be 103.2. Do you want to use the moment per meter number? Or do you want to use a total strip number? Which one would you prefer? Well, let me use a total strip number. Okay, so that's 103.2. Sorry, trying to write sideways here. Give me a second. So that's 103.2. Okay, then we've got external middle negative, so that will be here. Sorry, squeezing it in there. It's going to be 13.8, very little. And then we've got internal middle negative, which is here. And that one's going to be 43.5. Oops. 43.5. Does that make sense to you? Hey, why did this thing disappear? Sorry. Okay, 43.5. Right, so that's the way we put those moments. And then when we look at column positive, column negative, we do the same thing. So I've got, I need to put now, what color did we use? Brown. Okay, so you're looking at, first of all, where it is. It's there, next on the same line this side, but that 3 meters in that direction. Okay, so this one was 5 meters, the green space, and the brown space is 3. Sorry about the scale. And then column positive, let's put these numbers down. Okay, so I've got external there. I'm going to have an external here, and I'm going to have a middle there. So let's take the column positive first. It's 126.1. Hey, come on, man, stop jumping on. I think I have to get the scale to one thing and then it stops moving around. Let's see. Oh, no. Let me do it like this. I think it won't jump around. Let's see. So this one's internal column negative 130.5. Oops, pen 130.5, And then you got your column positive, which is 126.1. All right, and then your external column negative, which is 41.5. Okay, so does that make sense now?
So what about the half column strip in the 8-meter span?
The half column
Is that
strip.
only for shear?
Wait, let's go back to that one. So which strip you're talking about? Sorry, just again.
The
You're
half
talking
column
about
strip.
the half column strip that will be on the in the perpendicular span, because here there's no half column strips, right? The half column strip will come up here. Are you with me? So this band here.
Yeah, that's the same. That's the same one I'm asking about.
Yeah, so that is here. Sorry. I'm looking at the wrong thing. This one. Eight-meter span. Here we go. That's a half column strip. And this is the column strip here. Right.
Yeah, so we don't do moments for the half column.
No, but the brickwork is there, you see. You know, you have to have steel in there as well. He just hasn't included in his table.
Okay, thank you.
But what would it be? Okay, we come back to that question. What about the moments in here? What about the steel that goes there? What do we use? Is it the same as this one? Is it the same as the normal strip? Or is it different? Okay, let's put that on one side for now. Right, so we come to this one here and we've got all the reinforcement and you've got the minimums. You can see 2 of them fall below the minimum. Well, 3 of them, 4 of them. So all of these will get the minimum. So although you've calculated the area of steel, all that area of steel falls below the minimum. So for all of them, you're going to change it to 325. So you're going to put 325 minimum. You can't put less than that. So that's 325. That is 325. And as you can see, it gives us 10s at 225, mostly with 2 places where we just have 200. That's actually in the column strip only. All right. Okay. So, wow. We need to discuss the shear. I don't know why I didn't scan that. Okay, so let me just get to the shear part of it. Okay. Did I not include the shear part? Sorry. Oops. I think I might have. I just want to check if I've got the shear part scanned so we can talk about it. Yeah, we do. Okay, so we'll come back to that. Let's take a short break, 10 minutes. So we start at 20 past. Okay, we come back to the shear part at 20 past. Right, so let's take a small, let's stop the recording here. And we'll start it again.